Assalamualaikum to Encik Hakimi and my fellow friends. So today, me and my team members from Group 1 will present about our group project assignment, which is design and emulate a single cycle or pipeline CPU by given specification using hardware description language HDL. So our project title is implementing MIPS and the fetch and execute cycle.
There are 5 members in our group, which are Noratika binti Effendi, Chen Wanwen, Ahmad Muiz Hakim bin Rohaizat, Le Hong Yong, and Siti Nur Ain binti Zulkifli.
First is for introduction. So the objective of this project are to discuss the basics of pipelining and discuss the implementing of the MIPS pipeline. So to apply the concept of instruction execution in pipeline, it is required to break the instruction execution into different tasks. So for this project, we are able to design and emulate a single cycle or pipeline CPU by given specification using hardware description language HDL. So firstly, what we have to design is SR latch. So what is a latch? Latches are the fundamental bistable memory circuit in digital system to store data and indicate the state of them. So an SR latch, or the meaning of SR is set and reset, is an asynchronous device. It works independently of control signals and relies only on the state of the S and R inputs. So latches are basic storage elements that operate with signal levels rather than signal transition. So latches are sequential circuit with two stable states. These are sensitive to the input voltage applied and do not depend on the clock pulse. So flip-flops that do not use a clock pulse are referred as latch. Okay, so what is SR latch? So SR latch is S is for set and R is for reset, as I mentioned before. So they are also known as preset and clear states. The SR latch forms the basic building blocks of all other types of flip-flops. A gate SR latch is a SR latch with enable input, which works when enable is 1 and retains the previous state when enable is 0. So SR latch is a circuit with firstly they have two cross-coupled NOR gates or two cross-coupled NAND gates, and second is they have two input, S for set and R for reset, and lastly two output for Q and Q bar. Okay, so lastly, this is the design for SR latch. This is the coding that I'm using Verilog, and the result of the coding, which is the EP wave.
For the register, a register is part of the processor that can hold a bit pattern. On the MIPS, a register holds 32 bits. There are many registers in the processor, but only some of them are visible in assembly language. The others are used by the processor in carrying out its operation. These are the code that used to create the register, and below is the EPUF. The code demonstrates the basic concept of a MIPS processor register in Verilog. The testbed drives the register with some test data and clock, and the register file updates its memory based on the input. For ALU, it supports 6 operations in a combination circuit that calculates a 32-bit output based on two 32-bit input and a 4-bit input, specifying the ALU operation to perform. So this is the code to create the ALU, and its EPUF is recorded. The code provides a basic implementation of a MIPS processor ALU and a corresponding test bench. The ALUs test in two 32-bit input A and B, as well as an operation code OP, and outputs the result. The test bench provides a clock signal and initialize the inputs to test the ALU functionality. The test bench uses an EPUF signal to drive the clock and includes a few test cases to verify the ALU behavior.
Assalamualaikum warahmatullahi wabarakatuh and good evening. My name is Sama Musakim. I'll be presenting on state elements on data path and data memory unit. So for state element on data path, the code demonstrates a digital system which has a state element module and a test bench. The state element module is a Verilog design module that implements a memory element. The memory element has a 4-bit input state in a clock signal CLK, a write enable signal, and a 2-bit address signal. The output of the memory element is 4-bit Q. The test bench module generates a clock signal and sets a test state to two different values, for apostrophe B0001 and for apostrophe B0010. It also calls the state element module with input CLK, test state write enable, which is set to 1, address to apostrophe B01 and Q. The outputs of the state element modules are connected to the Q wire. The test bench module also generates a VCD dump file for waveform visualization. So for data memory unit, this code demonstrates a data memory unit with test bench with a design in Verilog. The test bench creates an instance of the data memory unit (DMU) and provides inputs, test data, address WR to it, and captures the output data out. This test bench initializes the input test data address WR and applies various values to them with time delays #100 to test the data memory unit's functionality. The design module implements a data memory unit with a memory array that can store values and retrieve values based on the value of the WR input. The dump file and dump vars statement create a VCD file to dump the waveform of the simulation.
Okay, next, sign extension unit. The TV sign extender entity has an input signal TB-SE in of 16 bits and output signal TB-SE out of 132 bits. The test band instantiates the sign extender unit UUT and map its input and output to the signal in the test bench. The process provides stimulus UUT by setting the input TBSE in to different values 0 times 7FFF, 0 times 8000 and 0 times FFFF, and waiting for 100 nanoseconds before changing the input again. The assert false statement is used to stop the simulation and report an error message and with severity failure when the simulation reached this point. Okay, for the marks, the testbed provided input cell I0, I1, I2, and I3. The marks example module check its output Y. The inputs of test bench are connected to the inputs of the module and the output to write a wire Y, and the test band display output and inputs, set input value, and run 6 simulation of random selector values, result saved in the dump VCD.
So I will present the part I, execute the complete MIPS data path. Based on the image shown in the slide, an EP waveform for the MIPS Verilog program is shown. A set of test bench Verilog coding is produced which acts as the highest level code to fill in the inputs to our design code. All the programs as SR latch, register, ALU, state elements on the data path, data memory unit, sign extension unit, and marks MUX is combined and run the MIPS program. And also the fetch execute process is used as the basic operation cycle of the computer central processing unit, which is CPU. There's two types of phase. First one is the fetch phase that we use This phase, CPU retrieves the instruction from the memory and loads it into the instruction register. And also the execute phase, CPU decodes the instruction and performs any necessary operations, writes the result back to memory or the register file. Hence, single cycle implementation, making it simple to implement but slower compared to the pipeline implementation. And pipeline implementation divides the instruction into multiple stages to allow the multiple instruction to be executed in a single clock cycle. So in summary, single cycle implementation is slower but easier to implement, while the pipeline implementation is faster but is more complex to implement. So for the part of conclusion, central processing unit, which is CPU, is typically made up of the main memory, control unit, and arithmetic logic unit. The ALU, which is arithmetic logic unit, register file, SR latch, data memory unit, sign extension unit, and mux are among the essential aspects required for carrying out the instructions. Making a single cycle or pipeline CPU, it depends on the design goals and trade-offs. So single cycle CPUs are simple to design and understand, but they are low performance because they only execute one instruction at a time. And on the other hand, pipeline CPUs can execute multiple instructions in parallel way, which this will increases the performance instead only for one instruction compared to the single line. Building a MIPS processor may be challenging but profitable. It has numerous of advantages for performance, portability, flexibility, education, and research. So we have come to the end of our presentation. Thank you.